Hi folks, this is a video solution for problem 22 in chapter 11, which is an instructional problem for this chapter. So let's get things kicking right off the bat. A 50-gram marble moving at 2 meters per second strikes a 20-gram marble at rest. Pretty straightforward prompt. First task is to draw a before and after picture of the scenario. So if we draw before and make some space over here after, we can say that before we have a larger marble coming in and it's going to hit a smaller marble. We know that the larger one is coming in at 2 meters per second, and I would draw, I'll probably label the actual masses here. So I would say 0.05 kilograms and 0.02 kilograms. It's key to remember that 20 grams is going to be 0.02 and not 0.2. That's 200 grams if we did 0.2 kilograms. And lastly, I would say that V equals 0. In the after photo, or picture if we will, obviously our smaller one, our smaller marble is going to be moving with some V2 final. And then I have my larger mass, and if you remember back in the very specific example of elastic collisions, that video lecture that I put up, since mass 1 is larger than mass 2, mass 1 is actually going to continue to move in the same direction, 0.05 kilograms, and we have V1F. So this is our before and after scenarios. Our next question is the system isolated or non-isolated? And then we want to explain this. So our system, this system, is isolated. Why? Why is it isolated? Well, whenever we think about non-isolated systems for collisions, we're thinking about interactions with a wall or a floor or a ceiling, the ground, some sort of interconnected external system that's complex, right? Our wall is connected to the rest of the building that we're in, which is connected to a foundation, which is in turn interacting with the earth around it, right? So we really need to consider all of these things to truly make it an isolated system, and that's very complex. So when we say a system is isolated, we're not interacting with a complex external system. There's no ceilings, walls, floors, something like that. Those are hallmarks of a non-isolated system. All right, so the system is isolated, no ceiling, floor, wall interactions. And what we can say then, if it's isolated, is that delta P is equal to 0. Remember that P is a vector, momentum is a vector. Part C, what type of collision is this? Explain. Hint, is there any deformation during the collision? Well, we're thinking about two marbles, right? If we're thinking about two marbles, they really don't deform much. They're pretty rigid. And so if they're pretty rigid and there's no deformation, what we can say is that this is an elastic collision. And I know what you're thinking, or I assume some of you will think this. I can't say that I know that you're thinking this, but I assume some of you are thinking, wait a second, marbles aren't elastic. They don't stretch and reform. But reminder that we're talking about the collision, not the actual object itself. When we say that this is an elastic collision, what we're actually saying is that delta KE is equal to 0. There's no change in total kinetic energy in the system before or after the collision. No deformation occurs, and there's no chance that these two marbles stick together to form a perfectly inelastic collision. So what is the initial momentum of the system now? What is PI? And reminder, we're working with vectors, so let's keep it in a vector notation. I'm going to say that the initial is M1 V1I plus M2 V2I, but V2I is 0. So what I'm really getting here is 0.05 kilograms times 2 meters per second in the I hat direction. That's going to be our default direction for a lot of things, plus 0.02 kilograms just to make the point, 0 meters per second. So I'm left with 0.1 kilogram meters per second in the I hat direction. This is our initial momentum of the system. Kilogram meters per second is the unit of momentum. And then, reminder, we need to have these vector notations, whether you use the I hat, J hat, K hat notation, whether you want to use in the X direction, in the Y direction, in the Z direction. That's a bit up to you. But that's our initial momentum of the system. If we go to the next page, what is the final momentum of the system? Well, we just said that this was an isolated situation, an isolated system. So if it's an isolated system, PI equals PF. And we can say that PF then is 0.1 kilogram meters per second in the I hat direction. It's that simple. It's that simple. And this is because the system is isolated. Otherwise, we wouldn't be able to necessarily do this. With the information given, I should say. Part F. What is the speed and direction of the 20-gram marble in this collision? So this system meets the conditions to use our special elastic expressions. I referenced that video lecture where we talked about this special case of elastic collisions, and specifically, right, M2 is at rest initially, right? That was our big condition to me. So what I can say now is that V1F is equal to M1 minus M2 over M1 plus M2 times V1I. And I can also say that V2F is equal to 2 times M1 over the sum M1 plus M2 times V1I. These were these expressions that I derived in the notes for a very specific case of elastic collisions. And we get to use them here. We get to use them because we satisfy the conditions. So the 20-gram marble is our lighter marble. It's V2F that we're looking for. And I'm going to say that I have 2 times 0.05 kilograms over the sum of 0.05 plus 0.02 kilograms times 2 meters per second, right? And when I throw, and really, I got to be a little bit more careful. I got to say that this is in the I hat direction because our vectors matter here. All right. And now, if I throw this into a calculator, what do I get? I get 2.86 meters per second in the positive I hat direction. That makes sense. It's going, it got pushed in that direction. What about the speed and direction of the 50 kilogram marble. So we're going to use this expression, this V1F expression. V1F is going to be equal to 0.05 kilograms minus 0.02 kilograms over 0.07 kilograms. That's our sum. Why not just plug that in? 2 meters per second in the I-hat direction. And bada boom, what do we get? We get 0.86 meters per second in the positive I-hat direction. So our initial guess as to the after picture here of this scenario was correct, right? Our V1F is still in the direction that V1I was moving in. So what we can kind of ask ourselves, does this give the correct final momentum? We know what that has to be, right? If I sum up the two momenta now of this final situation after the collision, 0.05 kilograms times 0.86 meters per second I-hat plus 0.02 kilograms times 2.86 meters per second I-hat. What do I get? I get 0.1 kilogram meters per second I-hat direction, which is exactly what we expect. So it's a quick check just to make sure that what we did worked out, and it does. Show that the kinetic energy of the system does not change after this collision. So let's just go by figuring out what the initial kinetic energy is. 1/2 0.05 kilograms times 2 meters per second quantity squared. I would write out the rest, but it's all equal to 0 anyways, right? The second marble is not moving. So what do I get? I get 0.1 joules of energy. It's key, it's a scalar here, right? Energy is always a scalar. I can think about KF. KF is 1/2 0.05 kilograms times 0.86 meters per second squared plus 1/2. Now I do have this other marble that is moving, right? 2.86 meters per second squared. And when I calculate this out, I get 0.01 joules. Really, if you do this out, and I encourage you to, you should. I got 0.1003 joules, but that's well within rounding limits. So I think 0.01, 0.1. What am I doing? What am I doing here? 0.1 joules and 0.1 joules. That all works out. So that is number 22 as the tutorial problem. If you have any questions, feel free to email me or swing into an office hour. Have a good one.